do kind of a general waste conversion technology session, and Tim Kelley is going to moderate the program with us. Go through this. I know Melissa is going to be our first presenter. She's joining us virtually, and then I think she has got to head out as soon as she gets done. So if it's okay, we'll have Tim, if you can have questions directed to her in case we have any questions, and then Melissa will let you sign off after that, okay? All right, Tim.
Okay. You know, first of all, I want to thank Gene. I can't remember how I found out about this conference many years ago, but ever since we started coming, Sean and I have said it's probably for dollar, hour for hour, it's the best conference we attend. We just came back from a conference with about 4,000 people in Washington, D.C., and as hard as it was, we are not going to come out with as many results as we are from this conference. So already I've met 5 companies today that are planning on coming to the Imperial County, and that's just an example of companies that are here, high in expertise, and ready to go. And so I look forward to working with all of you. But this panel, our first speaker is going to be Melissa Leung with GECA Environment. And she's virtual, as you can see. And then please hold up your hands if you do have a question, and I'll come back to you at the end, but I know her time is short. So thank you, Melissa. It's all yours.
Thank you, guys. I hope you can see me. I can't see you, so you let me know if it's okay. Just the first disclaimer, I got COVID about 2-3 weeks ago, and so I have a little remaining cough that might pop up as I speak, so please bear with me. But on that I will proceed. I'm just gonna share my screen, and hopefully it's gonna work out. All right. No, I know I'm young, but I'm actually pretty terrible with technology. So you guys, please let me know if you can't see it well.
Okay, you got it up there, Melissa.
It's good? All right. Well, thanks so much, everyone. And thanks a lot, Gene, also for the invitation to present. Unfortunately, I wasn't able to make it in person, but I really much look forward to the next time I can make it in person, hopefully next year. Today, I'm going to talk generally about trends in thermal transformation technology. So as Gene mentioned earlier, it's more of a general session. I have been at GECA for about 4 years. Let's just go. Oops, is it working? Okay, so really quickly, the outline, I'm just going to talk about GECA first. I changed the order. I think it makes more sense for your understanding of the data that I'm going to present. And then we're going to talk about trends in thermal tech, what we're seeing these days and how it's going and how it seems to be influencing the market. And then I also have short examples of technologies that just to illustrate the variability and the trends in the market. Okay, and again, as Tim said, don't hesitate to ask questions and direct them to me directly after the session. Really be a pleasure to answer them and have a discussion if we can. So first and foremost, I want to introduce our firm. As I mentioned, we are a consulting firm. Actually, I don't know if I mentioned it, but we are a consulting firm. We are very specialized in valorization of waste, so waste conversion into renewable product, valuable products. We specifically specialize in the thermal transformation processes of torrefaction, pyrolysis, and gasification. We're located in Quebec, Canada, so the black sheep of the Americas. We do speak French, but we actually have clients all throughout the world, including a lot in the US. Part of what we do is in really technical consulting, so supporting project development in business plan, choosing the right technology, right? Because we all know here there's a plethora of them, as well as process optimization. For example, I'm in business development, and I also lead the carbon team. So at GECA, we also do carbon project development and brokerage, specifically for biochar carbon credits. That's not the topic of my talk today, but feel free to ask any questions on the subject as well. Through our work, especially through our technology assessment and evaluation work, we have, I'd say gathered a long list of technologies within the processes that we specialize in. And so what I'm going to present today is data coming from knowledge of these technologies and in that list. All right. So everyone, I think, in the room knows what thermal transformation is. And I'm sure that people have, mentioned it earlier in the presentations. But just for the sake of this specific presentation, I'm mostly going to be speaking about torrefaction, pyrolysis, and gasification. So generally, we'd refer to very low amounts of oxygen in high temperatures throughout. That's really what we specialize in. And so the data that I'm going to present is specifically on these types of technologies. So here we go with the data. Through, again, our technology evaluation and we have a technology watch, we've listed more than 200 thermal transformation technologies. So TEX in gasification, pyrolysis, and of course in torrefaction as well. We've listed them throughout the world, but most of the stats I'm going to present today are for North American tech, specifically from Canada and the US. We've actually been putting together a technology report that lists these technologies and their characteristics. So some of the stats that I'm going to be presenting is coming out of that report. So what we're seeing is that there's approximately 120 technologies that are at TRL 7 or more advanced in Canada or in the US. So they have to have an office or headquarters in the Canada or the US for us to account for them in these stats. And we're seeing that the techs are mostly focused on large productions more and more. So this is the graph on the left, right, where we present that the size and the ratio of the distribution to the two countries. Now we're really seeing a lot of interest in larger technologies because smaller technologies have mastered the thing. Pyrolysis gasification is a known technology, and so lots of scale-ups are happening and tech providers. So that's what this graph or table is intending to present. And on the right, this is a table that presents basically the proportions of technologies that are catered for specific feedstock. So the primary feedstock and secondary feedstock that these technologies can process. And what we're seeing is that both in Canada and in the US, there's a large focus on biomass, conversion, whether that's wood, whether that's ag residues. We did put sludge separately, all right? But really biomass is what we're seeing come out. That being said, there seems to be quite a bit of interest in MSW processing as well as plastics and tires. But overall, we tend to see higher amounts of technologies in biomass. And I think that the reason is pretty simple. Most technologies in biomass actually focus on wood. And wood is a well-known product. It's not as nearly as variable as MSW or as sludge or even as plastics, right, in certain cases. And the process of often making charcoal, which is kind of the base, I guess, of pyrolysis, is where it started, has been done for a long time. So I think just by the experience and the knowledge in the biomass thermal transformation space, we see that translate in the number of technologies that are available in North America. Oops. Then we also looked in that report and in what we're doing into what those technologies are looking to produce. We have people here presenting today that are talking about, plastic transformation for liquids production, whether it's energy or chemicals. We have people talking about, solids, talking about energy, whether heat or gases or both. What we've seen in the US and in Canada is that there is a bit of a difference. There is a focus in the US on energy and gas. And so on this graph, we can see on the third column here that the paler bar is for gas. There is a larger amount of technologies, there are a larger proportion of technologies that have the priority is to produce gas. And our interpretation of this compared to, say, in Canada is that in Canada, energy is quite cheap. We're from Quebec. I know sometimes it comes out in the accent, sometimes it doesn't, but, raised in Quebec and in BC, for example, energy is super cheap. We have hydro, and in Quebec, we pay, I think it's 7 cents Canadian a kilowatt hour. Okay, and so there is not this need for large scale gas or energy. A lot of things are electrified and they use electricity, even industrial processes. Same thing in British Columbia and in big parts of Ontario as well. So the three largest provinces. Whereas in the States, electricity costs or energy costs are generally more expensive, perhaps except gas, right? But for this type of energy, that's what we're seeing. And there is a need for more gas production as well. So Canada seems to be more focused on the feedstock rather than necessarily on the products. So that's what we're seeing too. Now, aside from those stats, we work every day again in this market, and what we're seeing through technology assessments and evaluation for project development is that lead times have really increased for deliveries and manufacturing over the past year. Part of it seems to be due to COVID, part of it seems to be due to just larger demand in general, and also prices of components are increasing. I mean, I can't see you guys, but I think that if I say steel prices are high and are increasing and that's affecting those technologies, I'm sure you guys would all nod. So we're seeing a lot of that. And the pyrolysis gasification to our faction sector, we've seen lead times go generally from maybe, 6 to 10 months. That was prior to COVID, and let's say 2 years ago, to, 12, 14, 18 months for some manufacturers. So double the lead time. And that's, that can be a problem for project development and implementation. We're also seeing a lot of cost increase. Now, steel prices, again, inflation, labor is difficult. Manufacturing has increased a lot. So this is something that's affecting the whole industry. Another really large component that I don't know if it was discussed in the current, conference is the carbon market. We work every day in Biochar. I lead the carbon team in which we develop biochar carbon projects and sell biochar carbon credits. And that market has just exploded over the last 2 years. It is a new market, but the demand is so incredible that it's actually generating a lot of interest in those types of technologies, and manufacturers have orders piling up. I said that lead times have increased to maybe 12 to 18 months in a majority of suppliers, but I even have some contacts, collaborators in the field that they have a 2 to 3 year waiting list for their technology. And so that has really much affected the space in a good and also in some negative way. But overall, we're seeing increased interest, which is fantastic for manufacturers. Now, funding. I'm sure you guys are not strangers to this issue, but projects that use these types of technologies are difficult to fund through traditional ways. And it's still, we're still seeing the same thing. We thought that the carbon market would ease the funding structures and especially for projects that generate biochars as a main or as a co-product. But it seems like traditional, financiers are still quite wary about the carbon market. On our side, we are seeing some opportunities to fund partial projects with upfront payment or even equity investment for people who are interested in the carbon market. So that's really encouraging, but it remains still a big challenge in the market to this day. And lastly, war in Ukraine. I don't know if that was discussed again, but this is something that affects the strong quite a lot. It is in Europe, particularly, it's fast tracking some projects because they're very afraid that they're going to lack gas in the winter, right? And so it's fast tracking projects that use biomass to gas or even other types of feedstocks as well. We're also seeing that the war is generating, interest from large corporations into these types of technologies. So I'm sure you're also familiar with that, but it's kind of some light within the dark of what's happening over there. So now I just want to show this table. Last year I showed a similar table, but I modified it a little. I do want to say that price range has, the price range is large, as you can see, but prices have increased compared to this, to what I'm showing. And this is simply in the last 3 months, prices have changed again. And so my last inquiry with the manufacturers, may have, it may differ than when I had it. These are all technologies for large production. They're example. We didn't name them. GECA, actually, something that's important that I forgot to mention. We're very technology agnostic. So we don't have any links, any contracts with any of the technologies for bringing business to them or anything like that. It's very important to us to be agnostic so we could give out the best, suggestions to our clients, find the best systems for them. And so that's why they're not named. What I wanted to showcase here is really simple. It's just that all the technologies already all have different, characteristics in terms of reactor types, in terms of what they can accept as feedstock, in terms of size and products and pricing. Now, reactor types have, there's a wide variety, but they all have constraints and advantages to using them. It's really important to consider when we're doing a technology selection, right? What are you guys used to? What is the operator, more comfortable with, et cetera. We're also seeing that even for similar feedstocks, the products can differ, quite a bit. Again, we work a lot in biochar, so perhaps I have several examples here of technologies with biochar, but it's by no means the only product, even though it is, an important product when we're looking at these projects. And on the other side here, I wanted to showcase similar table, but for small productions. As I said, we've, calculated that, we follow more than 200 technologies worldwide. So these are just examples. There are feedstock and reactor types and size combinations for every technologies that do differ. So it's really important to choose the best one for a project. I want to say something else, but I think I forgot. So I'll come back to it later, perhaps. Frequent obstacle in these types of projects, feedstocks, really important, especially nowadays in the market. What we're seeing is that, especially in biomass, feedstocks are increasing prices, particularly wood. It's becoming more and more expensive, more and more difficult to generate projects with wood. And so we're seeing a lot of technologies move towards feedstocks like sludges, feedstocks like manure, and even mixed feedstocks. Can even look at some contaminated biomass as well, because it's becoming harder to make projects financially viable with wood. Now, carbon is helping there, so that's another market that is there. It's helping a lot, but still, in some instances, it's just it makes it much more difficult. Upscaling. Now, we've been having this technology watch for quite a while, and we're seeing more and more projects now go from a certain size and enlarging their system. But it's always a risk. The thermodynamics just sometimes don't work the same in the system. So what we're seeing actually in the market is systems are being designed for a certain size, and it seems like most project developers and even manufacturers are looking to add systems in parallel instead of upscaling to an enormous size. This provides a lot of risk mitigation. If you have a line that fails, then you can still produce using your other lines, right? And so this is really what we're seeing in the market. Oops, sorry about that. Public perception, not in my backyard. This still stands. For a lot of the projects, I'm sure for a lot of people in the panel and the conference, we still have a lot of issues communicating, what these projects actually do and how they do help the environment. Even if it's such an important component, it's not necessarily well understood by communities, and it's certainly not well understood by environmental groups either. So it's really important to have good communications with them. What we're seeing in terms of permitting and regulation is that there are changes that are occurring in mindsets of regulators. That DOE, for example, I think it was late last year, early this year, they issued an RFI on pyrolysis gasification so that they could look into reclassifying these technologies rather than them being classified under incineration. So that's a really good thing, but these things take time. So it's not necessarily for tomorrow, but it's really much encouraging, and we're on the right way. We're also seeing similar things in Canada as well, and in Europe, who are advancing actually much quicker than we are in North America. And so we do a lot of technology selection. I mentioned a few criteria that we want to look at, but let's not forget that choosing technology is one of the most important factors for a project. It will dictate CapEx. It will make or break a project. It will dictate what products come out of it. So it's really important to go through a really thorough process to choose the right technology for successful project. And so when we do them, we base them on multiple criterias, probably over 100, including things like security, which are not listed, and company history, and also experience. So that's just to keep in mind. That's perhaps one of the most important key takeaways. And lastly, before I finish, I work in carbon every day. So that's really my specialty. And I wanted to showcase for you guys at the conference how carbon has been playing a really big role in the biomass pyrolysis or gasification sector. A lot of really large companies are making pledges, are purchasing carbon credit, biochar carbon credits more specifically from these projects. So here, just to illustrate that, I've taken screenshots from Microsoft, from Swiss Re, the largest reinsurer in the world, Suez Group, NASDAQ that has acquired Pro Earth, Zurich Insurance, and Chan Zuckerberg Initiative, which is charity by the Zuckerberg family. Those are just examples. There are several others, but it's bringing a lot of attention to these technologies. It's bringing a lot of good attention to these technologies, a lot of opportunities. And it's really important for us to really put carbon at the forefront, because finally, these projects, these technologies are recognized for some of the good that they do. So that's really important. And if you have any questions on the subject, please don't hesitate. On that, that's pretty much it. That's what I wanted to present today. FYI, we are hiring. I know that a lot of people here are hiring, but if there's anyone present that would like to discuss about that, very open. On our side, I already presented what we did. We really work on a horizontal kind of all the way through project, whether it's business plan, through process development, through technology selection, through markets, and support with commercialization as well, carbon and the products. So I'll be really happy to answer any questions you have from now. So please feel free to ask in the room if you have any.
Okay, thank you, Melissa. Are there any questions for Melissa? Any questions? If not, I just want to say one thing. Earlier, I was trying to think of a word that when you're talking about public perception that you don't use, and I was working on a project many years ago, and every time we'd have a public meeting and the proponent would say reactor, everybody would look at each other like they're building a reactor. The other one was vessel. People didn't understand the word vessel, and so but when you're dealing with the public, you just got to make sure you phrase your words correctly. So Melissa, thank you very much. I look forward to meeting you in person, and so look forward to contacting you. Okay, so no
all right,
questions?
well, thank you very much.
Thank you. Thank you. Okay, our next speaker is topic, converting organic content-laden MSW to high methane content biogas and RDF. Glen Tobiason, and Glen is the president and CEO of InnoWaCon LLC.
Perfect. Do you want to give me the 20 minutes on that? How much you want? Yeah, I'll take a 20. Yeah, put a 20, then we know with some. Is this still on? Yeah. All right. Converting organic content of MSW, high methane content biogas, to high methane content biogas and RDF. We've heard a lot about that today. We discussed it in different sessions this morning. Is this also viable? Is it a SB 1383 compliant? We talked about California quite a bit. And I'm going to try to answer these questions for you. The simple answer is yes. We believe it is. Why? Landfilling, what's happening with landfills? We can go over that really quickly. Things are filling up. They're not being permitted anymore. There are no expansion permits, not going up, not going sideways. Housing is encroaching on landfills. It's a problem. Capacity, the siting, the waste hierarchy. It's not supposed to be going on landfills. You're supposed to be using the waste hierarchy to reuse, recycle, and dispose of it, and at the landfill is absolutely the last resort, according to the hierarchy. And also, you have to pose the question, what is the total cost of ownership of a ton on a landfill? And some might come out and say, oh, it's $40, $50, $60 a ton. That's my tipping fee. But what's the total cost of ownership out there? What's it going to cost you maybe to clean up the groundwater when your nice linings possibly break after 60, 70 years and leak into the groundwater? Who's going to pay for that cleanup? That's a total cost of ownership. It's a theoretical question. Of course, the liners do hold for quite a bit of time, but maybe beyond a certain legislative time. You know the new acronym NIMTOO. Do you know that? Who knows that acronym NIMTOO? NIMTOO. That means not in my term of office. So anything comes along, and we'll take care of it in my turn. When I'm gone, see you later. Yeah, that's it. Anyway, incineration, we know there's problems with that. It is a technology that's been out there and works very well. I'm not bashing incineration at all. It works very well. But there's the NIMBY and the age of facilities that are out there. They're getting old. They're going to be retired possibly. The Saugus facility, Saugus, Massachusetts, it's one of the oldest. It's run now by Wind Waste. They've had it for a long time. Was Wheelabrator, now Wind Waste. And it's getting old, and it's passing its time. They're trying to keep it going, but it doesn't really make sense. Citing any new technologies, any new incineration technologies, NIMBY, not in my backyard. We don't want it there. We don't want to see that stack. We're worried about all the pollution that's coming out of your stack. Okay, they do clean it up very well. So you have to, that technology's been around. They do work it very well. And again, the waste hierarchy. Why incinerate it if you can do something else with it better? And as I said about NIMBY. To do this, one has to answer other questions. What current sustainable, future-oriented waste treatment and recycling practices and methods are being used out there? We'll discuss that later in the panel today about waste conversion anyway. What do I do with my organics or my garbage? Depends on how you look at it. We call waste, and you have the garbage or the organics on the other side. What can be landfilled? What should be landfilled? Sorry about that. Go back one. What complementary technologies can be used? So technologies that go along with this to make sure it works in a very complete way. And these questions really have to be thoroughly addressed. A complete solution, you really want a complete solution out there, not just a piecemeal little project here and then, well, I don't know what's up front, I don't know what's out back. You want a complete solution to take care of it, combining the collection of the waste and the treatment and the recycling centers. And a very sustainable waste treatment process itself. The accent on sustainable. Recycling, utilization, and disposal of the waste products for these processes, you have to think about the whole thing. What's happening, the complete process? What's happening to this material that you're taking out and you want to recycle it and use for other things? Incorporating the complementary technologies and BAT. Who knows what BAT is? Or does everyone know what BAT is? BAT? Best available technology. Not just state of the art. I kind of look at it this way, that state of the art on a timeline, or looking from your side, timeline going, time over here, state of the art, it stays there, but time keeps on going. BAT follows in steps with time because it's always reinventing itself, always making itself better. One waste treatment solution is mechanical biological waste treatment, MBT. MBTs have had the challenges in the past. They haven't addressed all the concerns that I've talked about above. They were not complete systems, and they were difficult to control and maintain. Designed and built, maybe just enough to do the job out there, but not completely. And didn't extract the maximum energy and energy potential out of the waste to make use of this waste in the best way possible. They weren't sustainable. This resulted in unreliability, meaning the plants weren't working, they weren't staying online, they're having a lot of trouble as people are racing around trying to fix things, get it running again. Non-availability, meaning the plants weren't up 24/7 or weren't running all the time. You needed even more than 2 weeks fixing time, repair time to keep it going. And some of the facilities out there, they look like this. This is an acceptance hall. It's in Germany, of one of the facilities. Well, I don't want to work in that acceptance hall there. Look at the windows, all covered. The trash all over the place. It also depends on how you maintain your facility as well. In mechanical pre-treatment, these lines, work here? No, let's go back. These lines in the middle, those are cable channels. Cables are mounted in those channels. What do you see on top of the cables? All sorts of trash that is blown around, flown around, and landing in there. Things could get hot, could be rodents crawling around in there, chewing on a cable, not so very good, fire hazard. In the drying tunnels of certain facilities, that's one in Germany, that's a large drying tunnel. You can see it. You can see the vapor on the left side coming out of the tunnel. Those people are walking in there. I've seen them fill those tunnels with a small front-end loader. That guy doing it in a complete full gas mask, he was not a happy camper doing that job, loading and unloading. And there's material piling up on the sides, causing a fire hazard. More vapors in the drying hall. If you look carefully on the right side, one of the doors has come off its track. And so it's open, it's ajar, and you're talking about smells and dust. Materials or equipment that has been improperly placed. So if you have to replace a pump quickly, it's damn hard to get to it in some of these kind of places. And also environmentally unacceptable. Having a lot of this material outside, of course you have the outgassing, methanes, and other smells and odors, and very often places like that will be way out in the sticks, way out away from anyone, far enough away that you also have to transport some of your waste there, even more transport, and you know what that means these days, transport costs. These problems were addressed and result in what we call the maximum yield technology. It is not a product, it's a technology. It is sustainable. It is a tried and proven technology, not just new, not just rocket science, not just, I think this is going to work, tried and proven. It has been fully developed, well thought of. Before it was called MIT, it was the ZAC process. They worked on it and finalized it and said this is working. It is a flexible product with the inputs and the outputs. It's scalable. On the flexibility again, also on the inputs, such a plant will be designed to the inputs that are brought to it. It's not like this here, this device here, it's a product. It can only do one thing, one size, and the inputs, whatever, and outputs are defined. So you have to fit the inputs to it, or the outputs to it. Rather, this technology will fit to the waste that you want to bring to it, and the outputs what you want. Scalable, starting at around 20,000 tons a year. Let's say about the minimum size that you want, and up to 500,000 or more per year should be no problem. Eventually, you might get so large that you might want to split the plants in a large city. It's a German technology now available in North America, an MYT, maximum yield technology, is not a product, it's a technology, and it is BAT. These are the process steps. We like to look at it this way too. It is a complicated process, but it's done with the KISS principle. You know the KISS principle? Anyone doesn't know it? Keep it simple and stupid. Not keep it simple, stupid, but keep it simple and stupid. Where we have waste acceptance, a mechanical preparation of this waste, the biological conversion of the waste, the biological drying, mechanical material separation. This is a flow chart. I can go through fairly quickly on how this works. Left to right, of course. Waste acceptance, tipping floor. Won't be looking like this, but waste coming in. The waste is MSW with the organics. MSW with the organics. What does that mean? You don't have to have a separate organics bin to go chase after and have trucks going out there and people getting hurt. There's, as we heard this morning, it's a very dangerous, sadly, it's a very dangerous position to be in, be a waste collector. So if you have one less truck out there, one less person picking up this garbage, the organic waste, you are intrinsically safer working with it. Anyway, waste acceptance hall, MSW with the organics comes in, gets tipped out there. There someone takes certain large things. If someone throws out this pult here, or a table, or some chairs, or a motor block, we found everything in there, he can sort that out and bring it to the proper place. The waste that he wants, it's quite a bit of the initial volume, will go to the mechanical pretreatment side, where they also take out via trommel sieves and hand sorting. They take out certain materials like fuels, RDF, stones, metal pieces, glass pieces, and things like that. The rest goes into the biological step, which is our large mixers. We add processed water to this waste and mix it in large horizontal agitators. Mix it for max 2 to max 3 days. This waste then comes, that's after it's mixed, comes to a press where, like a sponge, squeeze that sponge. The water side goes to the water treatment, and this is where we make the biogas. The biogas from that, and that water that is used after making the biogas goes back into the system again as processed water, so very little fresh water. And the solid side goes to the biological drying step, where the solids end up as RDF, but in the biological drying step we have large tunnels, 5 meters by 30 meters long, horizontal tunnels. Put this waste in it, pump the air through it, it starts drying it out because we suction off the air, because there's a lot of biologicals in the water side as well as in the dry side. We dry this material out in 2 times 4 days. First 4 days in a tunnel, gets taken over to a second tunnel, automatic with a tunnel extraction device, coming to a second tunnel to dry out again to a final product of maximum 10% wet at the end. So a little bit wetter than this piece of paper. So on the RDF, I have some here on the table and outside on my table in the exhibition hall. After the biological drying, the solids go to mechanical separation, where we have different sifting and sieving devices and also densometric tables, so you get RDF and inert material coming off of it. That's a real quick overview of this work. What this can be done, and I don't know why it always does that, puts the glass to the right. Anyway, we have the black bin, the standard waste bin, and very often in Germany, this whole green or blue box, whatever color you see there, is how they do it in Germany. And you will find usually a bio bin, organics bin there. They call it bio bin. Organics bin in Germany, where you put your kitchen scraps. And we've heard today what happens with those kitchen scraps, or what do they find with them? A lot of plastics, contamination, stuff that is in there that should not be in there. In this case, the bio bin, organics bin, is part of the waste. There's no separate collection. In Germany, you also find the packaging is done by the yellow sack. All packaging materials should go in there, including cat food cans, cans of peas, empty of course, Tetra Paks, and the like. You will also find a paper bin with nice, clean paper to be used for the paper recycling industry. And also in town, a glass bin where you can put your different glass sorts in there, throwing it out like your beer bottles, other things. The Zack-Kallenbach plant in Ringsheim, Germany, they take those two as one. That's what comes into the MSW with the organics. But the MYT can take all of this. We just have to know to design it properly. We can have to know what's coming in. If you don't want to source separate at home, the packaging or the paper or the glass, something like that. If it's just to come in there and you get done with it, just bring it to us, collect it. We have to know what's in it, do a very good waste analysis of its contents and what happens over time. And we can design an MYT plant to fit the waste. Important. This is what it can look like. This is a waste acceptance hall. Right now you don't see waste up front. On the far left side you see some of the cans that we've taken out. We get around 4 tons of waste a year, and at this plant is 100,000 tons of MSW with the organics comes in here per year and gets treated here. You don't see the waste there right now, but every night they push all the stuff together, clean the floor, maintain the building. All buildings are under negative pressure, so air coming in, very little air going out. These are fast-moving doors. Truck in, door closes quick. So any of the smells, germs, dust does not come out. Mechanical pretreatment, step 2. Trommel sieves are on top there. There's 2 of these trommel sieves there to take care of the 100,000. This photo was taken in 2009. I was there at the time. I used to work at this plant. And this floor still looks like that. 2 young people run the 2 shifts a day. The whole plant runs 5 days a week, 2 shifts a day. 2 young people run this plant, and they're walking around doing their work, going from the trommel sieves, looking at different things, what's happening, and taking care of it, doing their sorting, and not running and to fix something real quick, because they do it ahead of time. Fix it before it breaks. Exchange a pump. Exchange a conveyor belt before it breaks over time. You know how long these things will work? Well, it's time to get the pump there to make sure it's still working. This is the biological step. These mixers. 2 to 3 days retention time in these mixers. Biological drying step, where the sludge from the fermenters also comes into here. So we don't have the problem with the sludge going out onto the fields with possible plastics and other things in it. The sludge ends up getting dried here in these tunnels. You don't see the tunnels, they're on the other side. Gets dried and ends up as RDF, refuse-derived fuels. The final step, step 5, mechanical separation. I think because of time I have to speed it up a bit. Outputs are biogas, 70 to 71% methane all the time. On the weekend, we put the waste in, maybe it'll be a little bit less quantity, but the percent methane is always the same, very high. Continuous uniform production of CH4. It might vary like this over the days, but it's not spiking up. Approximately 7% of the original input. So the Zack plant, around 7,000 tons of biogas per 100,000 tons that are being input there. Utilized, converted to RNG. We've heard a lot about RNG, what we can do with that. Converted to diesel, green hydrogen. Some might argue it might be blue hydrogen. Converts cryptocurrency. What? Cryptocurrency. You can't do that really with biogas, but ingenious idea. If you have energy sources, be it from this, or from wind turbines, or from, what are the other ones out there? Any sources that you don't need the energy right away, and especially from renewable energy source, like the wind turbines. You can take this extra energy that they don't need right away, put it into a box. The one side of the box has servers for mining cryptocurrency. The other sides provide the electricity for the servers. So they won't be using the electricity from the grid to mine their cryptocurrency, which takes a lot of electricity. But if you have electricity that's not being used and can't be used, well, don't turn off the turbines and just have them run, use the electricity. Kind of interesting way. I'm not trying to sell that stuff, but I think the idea is quite good. You can use the biogas thermally for electricity and heat. Other outputs are the RDF, refuse-derived fuels, 90% dry, as I said before, very, very dry. High calorific values, size dependent. This one I have on the table might be around 10,000 kilojoule per kilogram, depends on the size. The larger the size, the more calorific value. See, and there's the BTU per pounds. I believe that is the correct translation value. Someone correct me if I'm wrong. Utilized from a renewable resource such as waste into chemicals and RDF to methanols and ethanol. In the cement industry, they like it there in use in the kilns because it's less than 1% of chlorides in their cement. Power plants co-burned with coal. Okay, we're going away from burning coal, going away from co-burning with coal. Still is being done here and there, but could be used as such. Or its own RDF power plant, if they want that. But please do not landfill this stuff. It's too good to bury. Why landfill energy, a resource? Output, metals, extract the metals, maximum yield, extract the metals, bring it to a scrap dealer for sale, sorted by the different types of metals. Mineral sand, stone, porcelain chips, you can landfill them. What's nice about that, though, if you landfill them because you can't use it for anything else, the volume is considerably less. Here from this plant is around 10 to 11% of the initial weight coming in, but that's much less than the initial volume because it's much denser. So you can extend the landfill life just by putting on the inert materials. Maybe a base material for roads, and maybe for use in a new kind of construction material, kind of like an AAC, autoclaved aerated concrete, similar. The glass that you take out, you could bring it back into the circular economy if glass was now a resource. I don't think anyone could say that right now is a resource that everyone's looking for, so maybe landfill it. The plastics, it is yet, you could call it an enhanced MRF, but MYT is not a MRF. Utilize, sort them by type, bring them back to the economy, using pyrolysis gasification, as we talked about before. Making new high-quality pellets as possible. Thermally utilized, as we've said, chemically utilized, that was talked about before. The processed water that we have from the waste, because there's always water coming in with the waste, is used in the biological conversion step and then cleaned well enough so go into the local sewage treatment plant for further processing. Maybe some of it can be used also as a fertilizer, depends on the contents. We talked about PFAS before today. That has to be looked at. And it's clean enough for the local sewage treatment plant and can be used as the water source for some methanol processes, such as the company in Canada. This is kind of a breakdown. The 100,000 tons that the ZAC plant produces, or it takes in, produce around 38%, 38,000 tons of RDF, 7,000 tons of biogas, the treated water that comes out. There's some losses, minerals. You can see it. I have also some brochures out here if you'd like to see some more information later on. Cost to the citizen is kept low because it's a complete package, complete solution from the collection to the process to the getting rid of this material. Do it right the first time. A 4-person household in Germany, or in this county we serve, pays 91 euros, or let's say around $100 or 127 CAD a year for the complete process. Everything, the complete process. Collection, place for the plant, the 20-odd recycling centers we have, administrative paper pushers. And if one knows what one pays for the waste, and that's different than a lot of communities here in the States. If you know what you pay for the waste, and you get once a year a bill from the town, and it says 91 euros, and you know that if you create less waste, you can pay less by downsizing your bin, they're going to think of ways to, one, recycle more, and create less waste, which we actually all want in the long run anyway, creating less waste. You're going with the hierarchy very nicely. So people want, if they can save, let's say 20 bucks a year, that's a couple Starbucks coffees. Look at it that way too. There's some reference facilities we have. The one in Germany is the first one. It has been operating since 2006 with 100,000 tons, 105,000 tons a year, non-stop, no downtime, no 2 weeks overhaul time since then, and still operating. And the floors, except in Hall 1 where the waste comes in, are just as clean as this floor in here, all the time, except when they're doing some repairs and opening things up. One in Henning-Beaumont in France, close to Lille, 86,000 tons, been operating the same way since 2015, but the French waste is different than that German waste we have, slightly different. It was made to fit that waste. Onnut project in Bangkok, Thailand, 300,000 tons a year, operating since 2019, and the Thai waste is around 65 to 70% wet. It flows out of the trucks like a soup, and it was designed to take this waste. And talk about, that could be a very messy place to work in if you have that around your boots. And other smaller ones that have been built, and I believe they're building one right now in Vietnam. None yet here in Canada and in the States, but that's what I'm working for. We're trying to do that and bring this technology here. So this is do it right the first time with the continual improvement and process successfully lead to a better MBT process. Think about what you do in the beginning. Make it work. Maximum yield technology is that. It's a viable and sustainable MBT process. Reliable, high availability, meaning it's always working if you keep the process running, and like you're putting oil in your nice car. Oil, gas, water, keep things running, change the fluids. It's adaptable to the different sizes that you have. And if you want, for example, you have 100,000 tons now or 200,000 tons now, you design it now, and a couple of years down the road, you know you're going to bring in another county into your waste regime. Well, you design the space to the right or left of it, design the space to take it on later. You populate it with your machines now, and later on populate it with the machines to fill that later on. You can incorporate it into the local existing waste regime. You don't have to change everything to do this. Safe and clean workplace. OSHA likes you. You want people to be happy and working there and being healthy and working. It's hard to get people these days. Regulations, it'll be designed to the regulations. They will be upheld. And it's a very high diversion from landfill, of organics from landfill especially. And it's in line with the circular economy. Take out what you have to and bring it back in. And it is designed to fit. Not too big, not too small. Thank you very much. If you're interested, I have a stand over here in the exhibition hall. Come and visit me. We can talk, ask some questions there too later on if you'd like. We are also looking for people and companies and counties and municipalities that are willing to take on this challenge, look at MYT as a very viable solution in their counties in the US and in Canada. So with that, may I take any questions if you have? Okay. Thank you.
All right, thank you, Glenn. Remember, Glenn does have a booth next door, so during the break we could go over and talk with him. Our next presentation is demonstration of fast pyrolysis technology to make bio-oil and biochar from The County of Sonoma, Brian Gannon, founder, Biogas Energy Incorporated. Oh, it's
20 minutes? No. Great. Great. Well, thanks everybody for sitting in and listening to this. Biogas Energy was started as a biogas company. We built digesters in California. This is a project we built near Chico in 2019 that converts 100 tons a day of organic waste into RNG. So if anybody wants a tour of that, give me a shout. We'll come and take you and show you around up there. But that's not why I'm here to talk to you. Today, I'm going to talk about a project that was funded by the California Energy Commission. That's a state agency that really takes an active role in supporting cutting-edge technology development in California to address pressing needs. In this case, it was because, as you all know, California is going up in flames. There are millions of acres of woodland going with dead trees from drought and bark beetle infestation. So they gave us funds to demonstrate a pyrolysis technology that converts that material into bio-oil. So this project is operating today in Roseville, California, just outside of Sacramento. These are the feedstocks that we've done. Forest residues, so that's everything from slash, logs, anything coming out of Placer County's forests, urban waste, stumps, limbs, all that kind of wood waste, construction and demolition wood waste, converted over from bins that go from construction sites. They remove the wood from that and feed it to us. And then ag wood waste. So we tested out everything from almond waste to whatever comes off the ag side of it. We're currently testing biosolids and plastics at the bench scale, and then we'll do that at the demonstration scale early next year. So this is what we do. If it starts at the F for feedstock, fast pyrolysis in this case uses a combination of heat and friction to instantly vaporize the material. What you get is a biochar that goes down. That's the char at the bottom there. We get about 15% of the biomass converted to char, and the rest of it goes into a vapor. We call it pyrolysis gas. Now, when you take a vapor and you cool it, you can condense out the oil, the tar fraction, and that's what is bio-oil. The rest of the gas that remains in gaseous state is combusted to maintain the heat for the process. The bio-oil is about 70% conversion of the biomass in our process. So it's about 15% char, 15% gas, and then 70% converted over to bio-oil. And I'll go a bit more into what that bio-oil can be used for. We're also exploring this option, which is to leave the energy of the oil in the gas and use steam reforming to make hydrogen from it. So that's our next phase of development. But what is bio-oil? So this is the stuff coming out of the reactor itself. It's black, looks like crude oil, it's viscous. It's about 50% tar material and 50% wood vinegar. So Melissa talked about some of the outputs from pyrolysis. The wood vinegar is a natural organic pesticide. You can separate it out from the bio-oil, and then you have a cleaner oil to process. And the biochar itself, there's a lot of interest in biochar. It's carbon. So this is a skeleton that remains after you vaporize the material out of the wood biomass. And it's really good biochar. Biochar, you can see all kinds of gradations of biochar quality. Anything from 50% moisture content to ours is very dry, it's about 1%. 85% carbon is very good. So the process itself, although it doesn't make biochar as its primary product, it is a very nice byproduct. This is an aerial view of what we've operated there at Western Placer Waste Management Authority. So going from right to left, we've got a feedstock hopper. That's where the material is ground up and put into the hopper and dosed into the system. First, it goes into a dryer, so we get the moisture content down to what it needs to be for the reactor. It's conveyed over to the feeding module and automatically dosed into the reactor. From the reactor, the biochar comes out to the top left, and the oil comes out through the condensation module at the bottom left. This demonstration project does 20 tons a day of input. So after drying, that comes out to about 15 tons a day going into the reactor. We produce 1,850 gallons a day of bio oil and 3 tons a day of biochar. So what's the business model? We will put the reactors wherever the feedstock is sourced to minimize shipping and to condense the energy value of what we're going to access. So the biomass to bio-oil, we can locate them in the forests, in the agriculture country, at wastewater treatment plants, material recovery facilities for the wood waste coming out. And then the oil, what do we do with it? Well, we got a grant from the U.S. Forest Service to demonstrate using the oil in a boiler to make just heat. And they put us in touch with the Department of Transportation, U.S. Department of Transportation, who then forwarded the oil to a laboratory. And it turns out bio-oil is an excellent additive for asphalt and recycling asphalt, which is a big problem, I understand. This is all new to me, but doing tests through the Department of Transportation, the temperature variability is very important in an asphalt, as you can imagine, how it is managed in high temperature regions or low. And the bio-oil, adding 2%, it increases the range for the asphalt. Smoke flavoring, when you get bacon, you're actually eating pyrolysis flavoring there. So we've got a company that wants to buy all of the oil we can make to make sausages. And the wood vinegar itself becomes an organic pesticide when separated out from the oil. But when we talk about fuel, we're looking at partnering with Pacific Northwest National Laboratory to use the bio-oil in a gasifier to make sustainable aviation fuel, SAF. That is a big development right now because as all of our vehicles are going over to electrification and hydrogen and all that, airplanes, not so much. So as long as we can develop a sustainable aviation fuel, the aviation will be able to cut their carbon emissions, right? So PNNL, they have a gasifier. We're going to supply them with the bio-oil, gasify the oil to make the sustainable aviation fuel. But the big kind of brass ring on this carousel is to use bio-oil to replace heavy oil in conventional oil refineries because you don't need to make any changes to the equipment. You simply slip in up to 10% bio-oil to replace the heavy oil in the cracker, and you can just continue making your diesel and your gasoline from that. This is happening right now in Sweden, but we're in conversation with different refineries to demonstrate that here in the States. Hydrogen, of course, is also a big deal, especially in California. So the challenge there is to get a steam reforming system that's small enough that you can size it to 100 ton a day, 200 ton a day reactor rather than these massive ones that are at oil refineries today. So this is the system as it's operating today in Roseville. We designed it so that it is built in shipping containers so that when we deliver to the site, we hook them all together like Lego blocks, run the wires, do everything as needs to be done, and get this thing up running as quickly as possible. The big challenge for California and in a broader sense the US and Canada is the urgency of the issue and the massive demand for getting this biomass out of harm's way. So our approach is to not be finicky or try to make it too delicate. This thing is built like a tank, so we just push that stuff through, and we've got 2 guys on staff at any time. They're just fixing stuff as it goes. Pyrolysis has been around for ages. There's no need to make it too difficult to do. We're just there to push this stuff through as much as possible. This is operating at a MRF right now, and we're developing projects both in the Sierra Nevada forest and in the Central Valley for ag waste. Great. So I think that's all I want to say, but if anyone has any questions or anything, meet up with me afterwards. That's my email address if you want to get in contact with me. Happy to give tours of the facility, happy to answer questions either offline or today if we can catch up. Thank you.
Do we have any questions? Yeah, we got one right here.
Sorry, where did you say that facility was?
This is operating in Roseville, California, just outside Sacramento.
How long has it been operating, and what are the top 3 issues when it shuts down or you need to repair something?
We started operation in the summer of 2021, so it's been operating a year. The biggest issue we faced was contamination of rocks. Yeah. So when rocks got into the system, it would just hurt the machinery. Yeah. So you just had to maintain that. We solved that by being more selective about the material we put in. The rocks came from our attempt to pyrolyze the wood from compost rejects. Yeah. So you can imagine there are huge compost piles. They sift it, and they're left with wood byproduct. So we thought, well, let's take a crack at that. Bad idea. It had rocks get into the system. We avoid that now.
So a useful metric for a lot of these processes is energy return on energy invested. So can you provide that metric generally for both the pathways, the hydrogen pathway as well as the bio-oil pathway?
Energy metric, return on energy metric.
So energy return on energy invested.
Yeah. Well, to give you an example, that 1,800 gallons of bio-oil produced consumes 24 kilowatts continuous electricity, right? That's the only energy input. The gas is all self-generated to maintain the heat. So 24 kilowatts continuously, it's maybe $100 a day in electric.
Good enough.
Yeah.
Thank you. That was a very fascinating presentation. You said you guys are looking into basically using bio-oil as a substitute for heavy oil or diesel, right? So the calorific value, the VTU value, are very comparable? That's what your current research is indicating?
No. Yeah, the bio-oil energy value is about half of crude oil value, right? So it does not have, it's not a hydrocarbon bio-oil. Therefore, it doesn't have the same density of energy in it. However, the benefit of using the bio-oil is that it cuts the carbon emissions totality of that diesel and gasoline produced, right? So this is all early phase research that we're working with folks in Sweden to verify. But as a matter of course, the energy value in the bio-oil is about half of what is in crude oil.
And does it have to go through the same refining process, the raw, like the way the commercial oil goes through?
It does. So, well, what they're doing in Sweden is they're adding the bio-oil directly to the cracker, right? So this is way beyond my pay grade, the whole workings of an oil refinery. However, when you slip the bio-oil into a certain phase of the cracking process, it doesn't necessitate any retrofit of equipment, and you can just continue operating with that as the input. You know, like I said, this is the brass ring. You know, this is a big deal. If we can get all of this material out of the forests and replace oil with it, that's a big deal. But we're still early in that, especially here in North America.
I'm from Florida, and I've got a lot of debris from hurricanes that could go to this too. Any other questions? All right, well, I think we're going to break. Let's do this. We're 20 minutes early. Let me see if I can get the hotel staff. Do you all want to take a break, come back at 3 o'clock when the break's supposed to happen, or do you want to move everything up 20 minutes and be done today 20 minutes early? I'm seeing a lot of head shaking. All right, so I'm going to try to make that happen. So why don't we go on break? I'll get them to bring out some more coffee and some snacks, and we're going to try to move everything up. So we're going to be back here in a half an hour, okay?